although we've left it so long, there are now finally some signs that we're going to be heading back into space. We've got the Artemis program in the US, which will hopefully be sending human beings, perhaps some women this time, back to the moon. Other countries are getting involved, from India touching down on the moon a couple of years ago. China's got its own space station. And the work of the last few decades in astronomy and space science has shown us that there are many more worlds beyond our solar system to explore, not just the ones that orbit our own sun. And space is just really big. So, surely in the long term, we can't argue that humanity or whatever succeeds humanity's future will lie among the stars. This isn't to suggest that we can do an Elon Musk and try and avoid all our existing problems by just escaping to another world. But in the long term, it does seem like our future must lie there. And yet, if you go to one of my favorite websites, which is www.howmanypeopleareinspaceriightnow.com, the answer is 10 humans. And so what that means is, after 5 decades after the moon landings, we're in a place where about a billionth of our human population isn't standing on the surface of the Earth right now. There's about 1 million of them in planes, but they're going to be back down soon enough. So how are we going to get from this situation where only 1 in a billion people are anywhere near the cosmos to a grand future among the stars? Well, this panel hopefully is going to help illuminate that. We've got 3 speakers who are on varying degrees, as I said, of sort of depth into the extreme future. We've got Toby Ord, Anders Sandberg, and joining us virtually, we've got Jeff Sebo, who I think we can see on the screen soon. And what we're going to do is just quickly go through the panel, allow them each to introduce themselves in a sentence. And I'd also like to hear, what is the thing you are most terrified about with our future in space? So, Toby.
Sure. I'm Toby Ord. I'm an Australian philosopher based in Oxford. And I'm most terrified about squandering all of the resources of space, perhaps in some extremely costly race.
Anders.
Anders Sandberg, philosopher, futurist, academic, jack of all trades, active in Stockholm and Oxford. What fills me with dread with space is getting lost in it. It's so vast, and we have these pinpricks of stars and planets and moons. And if you could just fly around freely, like you can do in any software program to explore, it's very easy to lose your bearings, and then you lost Earth. And if you don't know where it is, you're not going to find it, because it's lost there among hundreds of billions of stars in the Milky Way. Space is so vast that our minds have a hard time comprehending that, and that fills me with a bit of dread.
And Jeff, what are you most terrified about?
What terrifies me, in addition to what terrifies the other panelists, which we are in agreement, is that space gives us a much larger canvas for causing harm. We have already caused a large amount of harm on our own little planet. Our own little planet is, of course, a very tiny fraction of the total amount of real estate there is in space. And so as we expand outwards, we can both create a large number of new beings and then interact with a large number of created beings and discovered beings. And that can give us the opportunity to cause orders of magnitude more pleasure and happiness in the world, but also orders of magnitude more pain and suffering in the universe. And I am very worried that we will take that second, more vicious path.
We've got 3 people with very different and quite, I would say, unusual perspectives on this. I don't think a lot of us have necessarily thought about our deep future and the moral implications of space exploration. So I thought the best way to do this would be if they each gave an introductory talk about their particular topic. We're going to start with Toby, we're then going to move on to Jeff, and then Anders is going to take us into the widest possible expanse of the universe. So we're going to have roughly 5 to 10 minute introductory talks, and then we're going to have time for a few questions, a bit of Q&A, and then we'll move on to the next talk. So, do you want to kick us off, Toby?
Sure, yeah. For the last decade, I've studied the risk of global catastrophe, in particular the risk of catastrophes such as a full-scale nuclear war or worst-case climate change, where humanity itself may be unable to recover. These are known as existential risks, and they're defined as risks that threaten the permanent destruction of humanity's long-term potential. This includes the risk of human extinction, a collapse of civilization so deep that we'd be unable to recover, a permanent global tyranny, or any other way that our potential could be destroyed forever. These risks would threaten not just our present, but our entire future. And that could be a long time. Humanity has existed for more than 200,000 years, 10,000 generations. So we've already survived 10,000 generations worth of risks from the natural world, which proves that the rate of natural existential risk must be very low. If we are destroyed, it would likely be by our own technologies. But if we can find a way through and reach a point of safety, then humanity could be just beginning, with millions of generations to come, perhaps spread across countless worlds. There's many different connections between existential risk and space, and I want to touch on two of them. 65 million years ago, an asteroid 10 kilometers across collided with the Earth. 1 trillion tons of rock moving so fast it struck with the energy of 100 times its own weight in TNT. In just seconds, it released the energy of 10 billion Hiroshima blasts. A billowing cloud of dust and ash rose all the way to the stratosphere and spread across the entire world, engulfing it in chill darkness lasting years. This shroud of dust and sulfates turned the regional disaster into a global catastrophe, ending the reign of the dinosaurs and annihilating 3/4 of the species on Earth. Asteroids are the most proven and well-known example of an existential risk. Those above 10 kilometers in diameter, like the one that killed the dinosaurs, threaten mass extinction. While it's possible that humans could survive the cataclysm, there is a clear risk of human extinction. Last time, all land-based vertebrates weighing more than 5 kilograms were killed. Asteroids between 1 and 10 kilometers across threaten global catastrophe and might also pose an existential risk, either via human extinction or an unrecoverable collapse of civilization. Astronomers have discovered and tracked so many near-Earth asteroids that we have a good idea of the total number out there with orbits that come near the Earth. We've found more than 95% of all near-Earth asteroids of size of 1 kilometer or over. And none of the ones that we've found has an appreciable chance of collision with the Earth in the next 100 years. We have even better news when it comes to asteroids that are 10 kilometers or over, as astronomers are almost certain that they've found them all, 4 of them, and that they pose no immediate danger. Taking all of that into account, the probability that in the next 100 years that the Earth is struck by an asteroid between 1 and 10 kilometers across is just 1 in 120,000. And the chance of being struck by one above 10 kilometers is just 1 in 150 million. And these probabilities are immensely reassuring. While there's still real risk, it's been studied in great detail and shown to be vanishingly low. It's a famous risk, but a small one. If humanity were to go extinct in the next century, it would almost certainly be from one of the other risks that we face. Indeed, asteroids provide the best example of humanity rising to the challenge of managing an existential risk. Many have claimed that if humanity could just survive long enough to spread out through space, that we would at last be safe, that we have all of our eggs in one basket. But once we become an interplanetary species, this period of vulnerability would end. This idea is based on an important statistical truth. If there are a growing number of locations which must all be destroyed for humanity to fail, and if the chance of each one suffering a catastrophe is independent of whether the others do too, then there's a good chance of humanity surviving indefinitely, as Anders has proven. Unfortunately, this argument only applies to risks that are statistically independent from each other. Many risks, such as disease, war, or tyranny, are correlated or would be correlated across different planets. If they affect one, then they're somewhat more likely to affect the others. A few risks, such as an unaligned artificial intelligence or the vacuum collapse, are almost completely correlated. If they affect one planet, they would likely affect all of them. Space settlement is thus helpful for achieving existential security by eliminating these uncorrelated risks. But it's by no means sufficient. Becoming a multiplanetary species is an inspirational project, and it may be a necessary step in achieving humanity's potential. But we also need to address the problem of existential risk head-on by choosing to make safeguarding humanity's long-term potential one of our central priorities. Thank you.
Thank you, Toby. So I'd like to talk about asteroids. I think that this is a risk that's very, very big in the public consciousness. And actually, we were talking just before we came on stage about the risk of this asteroid that's going to be passing by Earth in 2032. We now think very, very close and not actually hitting, but there's still an outside chance it might smash into us. Can you tell us a bit about how how do we know that's going to happen in all these years' time? And how should we be doing this better? Because it feels like quite short notice to have picked up on this thing.
Do you want to speak to the current one?
So 2024 YR and some number, it haven't got a charismatic name. It was discovered a while ago, and it's not a particularly big asteroid, but it would be a city killer. Were it to fall down on a city, it would be like a hydrogen bomb. Not a very good thing. And people got rather concerned when they saw the risk ellipsoid, where when you plot its orbit forward in time and with its uncertainty, you get a map of Earth and layout where it might hit. It kind of covered, wait a minute, Mumbai and Lagos and several very big cities with a lot of people that definitely don't want a hydrogen level blast hitting them. And then astronomers said, don't worry, we're very uncertain about this. We're going to make better observations and try to find out exactly where it's going. And that's most likely going to show that things are safe. And what you do is you try to observe its velocity and position on the sky. And these are uncertain observations you do with telescopes. But gradually you get a better and better plot of the orbit. You can simulate it forward. And that risk ellipse starts moving. Unfortunately, and the probability at first seemed to go up more and more, because as the uncertainty got smaller, the ellipsoid got tighter and tighter, and Earth was still in its sight. All the experts were kind of taking it rather happily. Right now it's 2% chance. Yeah, it's going to go down. Because they knew that once you get the final observations from a few of the observatories in orbit, which takes time to get the James Webb Telescope to look from a different angle and get enough data, typically it slides off Earth. And suddenly the risk that has been going up goes down to almost zero. There is a tiny risk that it might hit the moon, which might be an interesting show too. But basically, nobody was really worried in the astronomy community. And indeed, the planetary defense community, when I told them at a conference that, look, you got the best managed existential risk ever, they look very glum because they didn't feel like they were in control. But they're doing a much better job than we're doing on nuclear weapons and biorisk. But what you need is observatories in orbit rather than just sitting on mountains on Earth. And that's hard to get because there are few of them, very expensive, and quite a lot of them are orbiting Earth rather than orbiting the sun. We need a more presence in space to be able to see these threats.
I would add to that the asteroids come in a lot of different sizes. All the way from these 10-kilometer across asteroids, all the way down to ones the size of dust that just burn up before they would go through the atmosphere. And there are a lot more of the small ones than there are of the large ones. And so this one that caused recent headlines is much smaller than I was talking about. It's not the kind of thing that could credibly destroy humanity. Rather than being a kilometer across, I think it was 40 meters across or something like that. And the energy of these things is proportional to their mass, which is proportional to the cube of the diameter, right? Because a sphere is three-dimensional object, and so something that's 1 kilometer is 20 times the diameter. But it is much more than that in terms of
8,000 times. If I'm doing my maths correctly.
Yeah, I think that's right. 8,000 times the energy. And so the good news is that of the really big ones, we're going to get fewer surprises like that. We think. Bad news, perhaps, is that everything I said was about asteroids. We've done so well on tracking the asteroids that there's also risk from comets, and my guess is that there's now more risk remaining from comets. And so unfortunately, they're harder to do something about. They're harder to detect. They're in these very elliptical orbits where if this is the sun, where they spend a long time out here and then they zip through and then back out a long time. And you'd have to see them during this bit where they're going very slow and they're hard to understand what they're doing. And then they'd be coming straight at us if they were going to hit us. Which are very difficult to deflect because you also have to send a spacecraft out towards it on one pass in. So they've got a number of problems, and that's probably a frontier of things to deal with. And another aspect about many of them being small is that you will have heard about deflection programs. deflection works a lot better when they're small, right? As I said, that if they've got 8,000 times the mass, you need 8,000 times the impulse, to try to actually deflect these things. And the deflection methods that we have are actually inapplicable for any of the ones that are of the scale that could threaten existential catastrophe, which you don't hear about very often. The good news is that there don't appear to be any that threaten. The observational part has done its work, and we kind of have found ourselves to be luckily safe. So we don't need to do the action part because we probably at the moment couldn't. My guess is that storing food supplies and things like that in order to brace for the situation is probably perhaps the most that we could do. But anyway, it's quite an interesting aspect about the problem.
I think one of the frustrating things, Anders mentioned that space telescopes are very expensive. In a sense, they are. If you think about the James Webb Space Telescope, that was estimated to cost about $10 billion. But that's about $10 per person in the rich world. And I would really like not to be killed by an asteroid. I'd certainly pay $10 toward that noble cause. And obviously not just me, but literally everyone on this planet potentially. So maybe that kind of thing might be a worthwhile investment, even if it sounds like quite a big sticker price.
It also feels like, why are we just having one very expensive, very fancy, very beautiful space telescope? Why aren't we trying to make cheap and cheerful telescopes? One of the interesting things that is happening in space now is the new space, that we're actually launching way more rockets than ever before. We're actually returning to space because of various technological changes. And that might also mean that we can make space telescopes more cheaply, which we also need, of course, because the new satellite constellations are really wreaking havoc with observations the astronomers are doing. You think you might dislike Elon Musk, but that's nothing compared to what astronomers think of his Starlink constellation, because they're showing up in every picture all the time. So we might need space telescope to even be able to see out. So there is this interesting thing that being able to launch more stuff into space might both allow us to see the risk and do something about them. And of course, as some entrepreneurs have been saying, and usually going bankrupt some years after, mining the asteroids for getting stuff. Getting the space business going in the sense of not just communications and spy satellites, that is another conundrum that humanity is still kind of trying to solve.
It's very hard these days to spend a lot of time at a dark sky site where you can see the Milky Way, arcing over your head. But I went out to watch the Perseid meteor shower, thankfully all these little ones that are the size of grains of dust and burn up in the atmosphere in August. And it was remarkable to me how the sky is just crawling with satellites now. In any direction that you look, you can see these slow-moving things. They look like sort of dim stars moving in loads of different directions. And many of these are the Starlink satellites that Elon Musk has been launching, the other satellite constellations. And yeah, I think astronomers are very grumpy. And that does actually lead to some wider moral considerations, because this is impacting on our ability to view our sort of astronomical heritage down here on Earth. The practice of astronomy might even be putting us at existential risk by being less able to spot asteroids. So that, I think, is a wonderful segue to go to Jeff, because he wants to talk about some of the moral implications of spreading humanity and other forms of life, potentially even forms of artificial life, beyond the surface of planet Earth. So Jeff, can you give us an introduction to that rather incredible sounding topic?
Sure. So first of all, just checking that you can hear me. Can you hear me okay?
Good.
Mm-hmm.
Okay, excellent. I know you can see me, so all good as far as that goes. So yeah, thank you, first of all, for organizing this panel and including me. This is obviously an incredibly important, neglected, difficult topic. And thanks for your remarks, Toby. As I said when I was discussing what terrifies me, I think that we should take very seriously now in these early stages of planning and preparation the kinds of moral responsibilities that we would have, not only to safeguard a future for humanity, but also to safeguard a future for other types of minds and other types of life, and to ensure positive treatment of everyone who survives in this future or everyone who is encountered in this future. As we know right now, we already share the planet with a vast number and wide range of non-human animals who have at least a realistic chance of being sentient, able to consciously experience positive and negative states like happiness and suffering, as well as agentic, able to set and pursue their own goals based on their own beliefs and desires in a self-directed manner. That at this point includes not only all vertebrates like mammals, birds, reptiles, amphibians, and fishes, but also many invertebrates, including at minimum cephalopod mollusks like octopuses, decapod crustaceans like lobsters, even insects like ants and bees. And there are more than a quintillion individuals alive at any given time across those categories, across those scientific taxa. Now, we are already on this planet interacting with a staggering, unimaginable number of those animals at any given time, both directly and indirectly, both intentionally and unintentionally. That includes farmed animals, of course, and other captive animals. We right now farm more than 100 billion vertebrates in any given year, as well as more than 1 trillion invertebrates in any given year. Those are conservative estimates. And then we also directly kill trillions, if not quadrillions, of wild animals every year through fishing and hunting, through agricultural insecticides and other insecticides. And then if we factor in the effects of human-caused global health and environmental effects, including but not limited to climate change and melting ice caps and rising sea levels and acidifying oceans and flooding coastal areas and increase in the frequency and intensity of extreme weather events like floods and fires, you can imagine that human activity is now, in one way or another, to one extent or another, touching most, if not all, life on Earth in ways that are very difficult to predict and control. We are also, as we continue to affect more and more animals and biological beings, bringing into existence brand new kinds of minds, brand new kinds of cognitive systems through artificial intelligence. We now have chatbots that at least have the appearance of having a mind because they can generate realistic language. But more importantly, in order to create beings who can generate that kind of language, we are creating highly sophisticated artificial systems with capacities for perception, attention, learning, memory, self-awareness, social awareness, language, reason, flexible decision-making, a kind of global workspace that can coordinate activity across all of these cognitive systems. And experts, scientists, and philosophers are increasingly asking whether they might soon realize their own form of sentience, their own way to experience positive and negative states like happiness and suffering, whether they might soon realize their own form of agency, their own way of setting and pursuing their own goals based on their own beliefs and values. It might seem surprising that a system made out of silicon-based chips could have those forms of moral value, but we are not at present able to rule out the possibility that they could, and we are hurtling towards the creation of these systems. Now, the stakes of this predicament of being one kind of mind with one kind of experience and perspective, creating and controlling so many other types of beings with so many other types of mind and so many other types of perspectives, that is already an important and difficult predicament just on this planet. But we are now contemplating exploring new planets, exploring new galaxies with that same kind of predicament, that same kind of perspective. And so I think we need to take seriously the fact that the stakes could be significantly amplified and in a lot of familiar ways and in a lot of novel ways. So as we start to explore space, we might bring our current model of animal farming with us, subjecting vastly large numbers of farmed animals to the same kind of fate in space. We might also bring wild animals with us, subjecting vastly larger numbers of wild animals to not only the kinds of happiness they currently experience, but also the kinds of suffering that they currently experience. We might also bring AI systems with us in order to facilitate this space exploration, potentially subjecting them to lives that can be either good or bad for them. And we might encounter new forms of life. And we need to be prepared for approaching them with hopefully a little bit more compassion than we have approached other animals with when we first encountered them in the wild. And then I think that will confront us with this ultimate question of who is this space exploration for in the first instance? Is it for creating a positive future for humanity exclusively? Or creating a positive future for biological life more generally, or creating a positive future for any form of life that can have any form of moral significance at all, because that might affect basic decisions we make about how to optimize space exploration for success and how to safeguard it against failure. And without knowing all the answers right now, I just want to emphasize that these are very important and pressing questions, because if we just focus on how to explore space without considering the values and priorities that we bring into space exploration, then we are more or less guaranteeing bringing our old bad habits that resulted in factory farming and global climate change. We are more or less guaranteeing bringing those perspectives into how we design space exploration, and that could be calamitous.
So I was wondering, thinking about that, what do you think is your most likely technological vision for space exploration? Because when I think about this, and I'm absolutely not an expert on this, but it feels like it's quite likely that we're going to end up sending robots and artificial intelligences into space, because frankly, we're just bags of meat. If you accelerate us too fast, then we end up as very, very flat bags of meat, and so on. And so it's perhaps going to be easier to send, robust silicon computers. And irrespective of that, whether you are thinking about biological exploration in the longer term, more like one might see in a film, what kinds of moral considerations do we need to make in the here and now in order to try and make sure that your vision of space exploration goes well?
So if the question is directed at me, then I will just, first of all, say that is a very good question. And second of all, say that it raises really challenging questions about creation ethics and population ethics that I touched on towards the very end of my remarks. And these are high stakes questions. So the question here is, what kind of population do we hope to see in the distant future? Are we imagining, for example, a smaller population of beings who look and act like us and are made out of similar materials as us? Or are we hoping to see a perhaps much larger population of beings who look and act much differently than us and are made out of much different materials than us, but could exist in much larger numbers and in a larger number of spaces? And that really matters, because if we optimize for the survival and flourishing of biological beings who look and act like us, then we might be building very different types of spacecraft, and we might be filling them with a smaller number of organic biological beings, and then really trying to empower those beings to survive and flourish in smaller numbers. Whereas if we feel okay letting go of biology, or at least not optimizing for that, then we might be designing very different types of spacecraft and filling them with much larger numbers of beings and sending them into much different types of spaces that are less hospitable for organic and biological life, that are but are compatible with the flourishing of this new form of digital life. I think we are not right now equipped with the philosophical and scientific frameworks that we need to think through those issues with sufficient rigor. And there's also a risk that we will either just let a kind of human-centric bias prejudice us against other forms of life that could have a large amount of intrinsic value, or let simplistic, reductive mathematical thinking bias us in favor of just optimizing for happy, efficient digital minds, even if that could be really too simplistic and too reductive, and it could cause us to just lose really important and difficult to replicate forms of value that exist in biological beings. So my initial answer to your question is just, we need a lot more research, and that requires patience, and that requires scientists and philosophers and policymakers thinking together just about these basic questions involving what kind of value do we hope to see in the future, and how should that affect our policymaking and priority setting in the short term.
Obviously, there will be technological constraints. We should certainly be placing the sort of ethical and moral considerations front and center when even deciding what technologies to develop, let alone shooting things out into the universe without any prior thought. Toby?
The stakes of space are extremely high. That is this kind of giant multiplier on everything that we could achieve, whether good or bad. Ultimately, there are, we're on one planet, and there are more than a billion other planets in the affectable part of our universe. It wouldn't be surprising if that is substantially more important than what happens here, if we go out and do things with these other planets. Or if we don't, if we choose not to, then maybe renouncing that opportunity is like a grave mistake. And we're so far from understanding what to do with all of this. And something that's very concerning is that with the developments of AI at the moment, I think it is quite possible, not a foregone conclusion, but quite possible that technological discovery will speed up substantially, let's say to something like 10 times the current speed, so of breakthroughs per year within the next decade. In which case, if you see, a century worth of progress in a decade, then it could just be 10 years before we have the technologies needed to automatedly settle space, to travel to the nearest star and then send out more probes to places beyond that, because this would be AI-powered technology, and so these spacecraft would have AI on them and wouldn't need to kind of bring a human body over that distance. So that may be upon us much sooner than we typically think. And my advice ultimately would be, I just don't think we're going to know the answers before that's upon us. And I think we can't put things in a situation where someone could unilaterally take those choices, where there could be, say, a billionaire or a particular country in the world that decides, you know what, we've worked out how to do this very clever von Neumann probe self-replicating thing. Isn't that interesting? Let's push the button and then possibly turn our whole galaxy into something that the rest of the people on Earth would be suspicious of, and which on reflection we'd discover was a terrible mistake.
Yeah, and talking of Elon Musk, we've already seen this in our backyard. And I think this is actually a perfect segue to Anders' talk.
Okay.
Because you want to talk about
the really big stuff.
The really big stuff, and what happens, when we do start sending out these potentially self-replicating artificial intelligent probes, and what is the grandest possible future going to look like?
Oh dear, you asked me about the grandest possible future. That's kind of like catnip for me. But if we start out right now, this conversation really is affected by the Outer Space Treaty, which was formulated in an era where only superpowers could reach space. So there was this assumption that, we can declare that space is the common heritage of mankind. We want to have peaceful scientific exploration. And the treaty is basically structured based on the assumption that, it can't be smaller nations or companies or individuals that go to space and do things in space. So that treaty is under a tremendous strain already. It's also worth noticing that it doesn't exactly say that you're not allowed to spread life in space, but it's kind of part of the COSPAR treaty dealing with the scientific exploration of space that is basically telling all the world scientific academies to handle it. And in their joint protocols, there are rules about sterilizing space probes that might go to planets that might harbor life. The motivation for this is, again, not to put Earth life there so we confuse it for native life, because the real the issue might be we might want to explore for life. But it's also understood, of course, that as soon as we send more stuff there, and eventually people, sooner or later somebody is going to get a puncture in the spacesuit, and then the bacteria out in that environment. So that treaty is only a stopgap. And we don't really have a treaty about how to handle the spread of life in the universe. I have a paper coming out in Acta Astronautica with Asher Sorrell about the ethics of directed panspermia. The idea that we might deliberately spread bacteria to other solar systems to seed life, which to some people, I belong to that group, think this is great. This is one of the best things ever we can do. Asher MacArthur thinks this is one of the worst things we could possibly do. Think about all that wild animal suffering. And it was very fun to work through this and realize, we both support an idea of having a moratorium on spreading life in space. That is actually something that we might want to put off because, if it is the best thing ever, we might actually wait 10 years or 100 years or even 1,000,000 years. It doesn't matter very much on the cosmological timescales. So we might want to put it off until we solve philosophical and coordination problems. And that shows that if we can figure out good ways of exploiting the solar system, I think we can do it in a useful way. But that's something that's going to be decided over the next few years. At the same time, as Toby points out, we might get tremendously much more rapid technological progress. Self-replicating robots might sound like extremely weird science fiction. They're not terribly fashionable in robotics, but many people realize that actually, if we want to build stuff on the moon, we need to use local materials because even with the best rockets, it's expensive to launch things into space. It's much better to use the moon dust and actually make things out of that. So there are projects like Blue Origin's Alchemist that are working on making solar panels out of lunar material, which of course could power a lot of equipment. People are interested in, can we make electronics out of lunar material or other useful things. Alex Ellery, engineer and professor in Canada I'm collaborating with, is working on questions about lunar self-replicating robots that are solar powered and build more robots and more solar panels in order to build large energy parks to supply Earth with clean energy. But of course, I'm thinking, I want to put them on asteroids and then convert the asteroids in solar panels, encasing the sun, building a Dyson swarm, collecting all of the sunlight. Now I get 10 to the power of 26 watts of power, which might power a few computers and other applications. We might need that if we want to build more data centers for our AI. Or more worrisomely, the AI might say, that's great, we want that. And we humans might wonder, why did it get dark so quickly? There is a real issue here with these kind of technologies that give very strong first mover advantage. They're also interesting because self-replication is something that allows a very small investment in matter. It needs to be carefully put in place, but if it's done right, it can convert arbitrarily large amount of matter and energy into other shapes. As we've seen with Earth's biosphere that has totally reshaped this planet. And it didn't do that with much planning. It took it literally billions of years. But we could probably design technology, whether biological or artificial, to reshape planets, to reshape solar systems. And indeed, instead of sending a big starship with astronauts to a near star system, the most likely way is you send a solar sail where you have some small amount of nanomachines. You use lasers from your solar panels in space to beam onto that, send it over. It might take a long while by human standard, but once it gets over to the other solar system, it lands or just slams into an asteroid, converts that into solar panels and more robots, etc. And now you can replicate across the Milky Way. Turns out that under fairly conservative assumptions, it takes about 40 million years for this kind of system to spread across a galaxy, if you're not pushing it. If you're pushing it, faster, a few 100,000 years. You can also see that you can do this with other galaxies. So Toby mentioned the affectable universe. Basically, there are galaxies out there that we can never ever reach because the expansion of the universe is accelerating as far as we know. And that means that there are some of these galaxies that even if we send a light signal, the galaxy will run away from us faster and faster. So the signal will never reach it. No spacecraft we can ever make can ever reach them. There are closer galaxies that we could reach with fast spacecraft. So there is this sphere, which is about 16 billion light years large, that we could reach if we so choose. That is what physics allows us to change. What we change it into is very much dependent on the values of whoever sends out these self-replicating systems. And that might be artificial intelligence, it might be humanity united under the United Nations, it might be a despot, it might be a lot of different actors or cultures. It's undefined as yet. There is nothing in the laws of physics telling us what this process, this phase transition of matter into life and technology has to look like. There are laws of physics limiting us with light speed limits, dissipation of heat energy. There is a lot of things that keeps engineers up at night. But the shape of the long-term future is actually set by intelligent values, evolution, markets, many of these forces that are rather remote from the fundamental laws of physics and much more amenable to human and maybe post-human and animal decisions. If life can spread away from, if we can survive on Earth, if we fix existential risk, we might, as a normal species, survive for 1 million years before a normal natural disaster takes us. But if we solve our existential risk, we can probably handle even mass extinction risk. So we might very well survive until the end of the biosphere, which is in about 1 billion years, give or take a few 100 million years, depending on your climate and solar model. But there are some ideas on how to fix that. If we were to just settle the solar system, we could survive for about 5 to 7 billion years before the sun turns into a red giant. Where we or our descendants to spread across the galaxy, stars are going to be shining in 1 trillion years. Barnard's star, which is kind of next door, about 10 light years away, is still going to be dimly shining about the same intensity as it currently is. in 1 trillion years. It's going to wink out in about 10 trillion years. That is the kind of time spans we get if we just set it around stars. And of course, then AIs are going to say, you meatbags, you want it so hot and warm. We prefer cooler temperatures. And now in 1 trillion years away from Earth, oh, it's finally cold enough to really think clearly. Now in the autumn of the universe, the real good stuff can begin. So they look forward to the day when the stars are burned out and the real clever thinking can begin, which can last for timescales up to 10 to the power 36 years, beyond which current physics suggests that matter might not actually be stable. But intelligence has plenty of time to think about solving that problem. These are enormous numbers, very unfathomable timescales. It's very likely that we're wrong about many of the fundamentals. But again, Jeff's point about that our actions can be mirrored by an enormous future, enormous amounts of things. That gives us a reason to think about the Artemis Accords. That gives us a reason to think carefully about how do we update the COSPAR rules? How do we handle private space flight? Could we implement at least a brief moratorium from spreading bacterial spores in space till we understand the situation better? Can we find a way of handling the responsibility for redirecting asteroids? And these things are practical diplomatic missions. These things are stuff that you can talk about in Geneva. These things you can do at the International Astronautic Symposiums. These things can happen now. And the rules we set up now are going to affect how we go about doing space for the next few decades, which might very well then echo down literally the eons.
And it's quite interesting to me how the decisions that we make today about the nuts and bolts of legal stuff and morality can really potentially echo through the ages, and how this could matter. Maybe it could be the next 10 years if artificial intelligence is very fast, but it could well be the next couple of centuries, which is a blink of an eye in cosmological terms, considering our part of the galaxy has probably been free from life for the last 10, 13 billion years. And yet here we are, debating these things that could happen within the lifetimes of people alive today, potentially.
So we don't know whether quantum computing is going to change AI. That depends on in theory, there is a lot of useful uses of quantum computing for making AI even better. In practice, we don't know whether these will play out and get scaled up well enough to really matter. What I think is interesting is quantum computing has this property that is logically reversible. That is, if you perform a quantum operation, you can also unperform it, moving the bits back to the original state until the point where you measure it. This is important because classical computation, every time you erase one bit of information, you need to pay a little payment to Maxwell's demon in thermodynamics. You need to dissipate a little bit of energy as waste heat. In the really far futures I was talking about, this is the main limiting factor. Those post-humans or AIs of a far, far future, they're going to be very careful about their energy in their very cold universe, because when you use it up, it's gone forever. And eventually you will have used up all your energy if you're not careful. With quantum computing, they can perform computations that don't cost energy because it's logically reversible. If you do it carefully enough and don't get any errors, you can actually use much less energy. You can suddenly probably do an exponentially larger amount of computation. Toby's and my friend Adam Brown and me, we called this the Vigintillion-plex hypothesis. It looks like theoretically you can do about a vigintillion computations across the future of the universe we can affect. That is 10 to the power of 120, which is a ridiculously large number. But if you could do this with quantum computer, you can probably do it to the power of 10 to the power of 10 to the power of 120, which is a ridiculously large number. It's actually limited because of various aspects of quantum gravity to a somewhat smaller number. But it looks like the future suddenly got even more ridiculously large. So if quantum computing is a thing, the future matters even more. But right now, we still have a question of can we scale it up enough for our own purposes? And the really practical thing, if we get quantum computing in the next few years, there's a lot of secrets we have from the previous 10 years that are going to be crackable. And they're probably saved up in various intelligence agency archives around the world. So we might want to think about the practical security we get from that too.
So my worry is about even getting past the next 5 years, 10 years. So I love talking about the future is ahead. But the geopolitical risk of anything that we're doing in space, from LEO to GEO up to cislunar, is acute. And we can talk a lot about what the UN could do or how we could have some treaties. But the second helium-3 is discovered on the moon, is anybody going to pay attention to UN treaties? And so how do we address that very real geopolitical issue?
I'm less worried about helium-3 on the moon because because the economics doesn't make sense. But I agree. The scariest thing about near-Earth orbit is that everything is moving as fast as a rifle bullet relative to each other. And it's very fragile and it's expensive. And a lot of it is military equipment that involve early warning systems for missiles and a lot of other stuff. This is a nightmare of mistakes just waiting to happen. And I do think that this is something we need to figure out a way of dealing with.
Yeah, I mean, so on the moon, there are a number of scarce locations. There might be these peaks of eternal sunshine, and where it's always a very small amount of area that's always hit by the sun, and various other rare locations. And there are questions about how close, if someone goes and claims it, can other people come in there, or will it be effectively a territorial claim, which is not allowed under the Outer Space Treaty. But I like your general point as well about the kind of real politic of this stuff. That I think it's important to get the space law right, and I think that it has some impact. But it's a mistake to think that it just governs the future. Ultimately, there are some ways, as you pointed out, where this could be bad because we could get the space law right, and then just the largest country just does what it wants anyway. But there's also some ways in which it could be good. So suppose we haven't sorted out the space law, and potentially some country, just starts exploiting space resources, perhaps using it to build more machines that do more exploitation. The government of that country is still on Earth, and if they are not that powerful compared to the rest of the world's countries, then the rest of the world's countries can lean upon them and say, stop what you're doing there. It's not as important as us cutting off all trade with you or various other things we can do. So at least it's also potentially a fallback, especially if there's one country that's doing a clearly wrong thing and others can pile up against them. Not so good if it's one of the two most powerful countries or if they have nuclear weapons there.
I just thought I'd quickly explain what these peaks of eternal sunshine are, because I think this is absolutely fascinating. At the south pole of the moon particularly, there are these large deposits of water. So you might be thinking, we're going to go to the moon, we're going to mine gold and platinum and titanium and helium-3. But actually, one of the most valuable resources for human settlement on the moon is going to be water. And so deep in these craters, the fascinating thing about the moon, most bodies in the solar system, our Earth, for example, has an inclination. So the orbit, the way it goes around the sun, is tilted by 23 degrees. And that's why we have seasons. But the moon is almost exactly straight, which is just crazy to me, because if you look at every other planet, they're wobbling all over the place, essentially. And because it's so straight, that means that these craters that are deep in the South Pole, imagine they're right on the bottom of the globe, they're constantly in shadow, so water ice is able to stay there for billions of years. And then the mountains that surround those craters are then constantly in sunshine. And because of the way the moon goes around the Earth, most locations on the lunar surface are dark for about, 14 days or something like that. And then bright, blaring, cooking sunshine for the next 14 days and so on, which is a very challenging environment to work in. So it means that, perhaps the most valuable resource on the moon could be these tiny mountains just around the South Pole. And so we really need to come up with some way to get the space law right to make sure there isn't a race for those.
Some good news on that regarding, is that the US is in a strong position to just go there and perhaps before law is sorted out, and perhaps just to bluff other countries by saying it's just going to do something. But there is something they really care about, which are the Apollo landing sites as sites of historical interest. And so this is potentially going to be one of the main kind of bargaining chips with the US if they want to be able to preserve those locations. If they say it's just anyone shows up and does whatever they want there, if they set that precedent, then there's something at stake for them.
Thank you to all three of you for these philosophical perspectives on space exploration. And let's hope that we can unlock some of these incredibly grand futures. And thank you very much, Dragon, for coming.